Alright, welcome to the NUPOC video study guide number 58. So like I had mentioned in the last video, we're going to take a little bit of a detour from just plowing through all the study guide problems like we've been doing up to this point. And I'm going to focus a little bit on some key topics in calculus and physics and engineering and such that I think will really help develop some tools and techniques for you that you can demonstrate to your interviewer when you go to your interviews, and it's really going to prepare you much better than just giving an equal weight to every problem in the study guide. And you know, we're going to go a little bit deeper in some areas, right, instead of going broad in everything. And one of those topics I think is important is implicit differentiation, because it's a great tool that can make otherwise very difficult calculus problems very easy. And it also forms the foundation of related rate problems, which are very important because they are in turn the foundation of optimization problems, which are one of the biggest calculus applications in engineering. So anyways, these are some important things, and we'll get to that. Eventually we'll do problems in all those, but for now let's start with implicit differentiation, which is essentially just the chain rule. And we'll show that when we go through this problem here. So these problems, some of these problems, most of them will probably not be from the study guide, because the study guide maybe has one or two problems on implicit differentiation or related rates and such. So we're going to go in and we're going to go deep, a little bit deeper into some of these areas. So I'm going to be taking problems from other material. I know in the previous video, number 57, I linked to a web page for a calculus text. It's in fact the calculus text that I used when I was taking that class, and so it's got some good worked solutions there and whatnot. This problem, I think it's from there. I can't remember, but I like this problem. So let's get into it. So we want to find the slope anywhere on the curve x squared plus 4y squared equals 4. Okay, so this is a problem. I don't know if you can kind of tell by intuition, but this would actually be very difficult to find the slope or the derivative of this function, right? If this is if we moved everything to one side and we said this is f of x, right, and then we said or we made it y equals whatever. In fact, it would come out to be we would actually say y equals plus or minus, I believe it's 1/2 root 4 minus x squared, okay? And if we wanted to say, okay, well, what's y prime or something, it would actually be kind of difficult, right? Because we've got this plus minus, so we've actually got to take, it's sort of like a piecewise function, and we've got the root in there, so anyways, it would be more steps. So we would want to apply implicit differentiation in this case. And before we do it, I do want to take a look at what this curve actually is, right? So probably some of you can see it from intuition, right? It's some sort of it's probably something like a circle, right? But not quite, because if it was x squared plus y squared equals 4, that would be a circle with radius 2, right? But here it's a little bit distorted, right? Because you have this 4 on the y, so it's an ellipse. So if we were actually to plot this, we would have some ellipse like this that goes from x equals -2 to 2 and y equals -1 to 1, right? So it's doing something like this, okay? Well, that's not a very good drawing, but you get the idea, right? So we want to find the slope anywhere on this, so it's kind of, it would be difficult to do it directly, because, here we've got, a very low positive slope. Here we've got a discontinuity, right, where we have essentially like infinite slope at the ends here, right, where x equals -2 and 2. We've got 0 slope here at 1 and -1, and but then we've got two values of y for every value of x, which is where we have the plus minus here, so we'd actually have to do two differentiations. So it would become very complicated if we wanted to go, or not very complicated, but it would be more complicated if we just brute forced it and moved everything to one side and said y equals and then found y prime, okay? So when we have curves like this, right, curves that overlap, or a circle or an ellipse or there are even other crazy curves you can do. It's like a figure eight and all kinds of different things, right? Or a hyperbola. We want to go with implicit differentiation. It's going to be much, much easier. So let's get into it. All right. So I have this equation here. So I'm just going to take. I want to find dy dx. Now we could also find dx dy, right? But we can do that at the end by just inverting it. So let's find dy dx, right? And so what we're going to do is we're just going to take the excuse me, the d dx of both sides, or of every term, you know, because it's a linear operator, we can just apply it to every term, right? So I'm going to have d dx of x squared plus d dx of 4y squared equals d dx of 4. Now something to remember here is, and in fact I was just discussing this in a reply to a comment I had on an earlier video talking about implicit differentiation. If you use implicit differentiation, you have to assume that x and y are coupled, right? So here x is a function of y and y is a function of x, right? But theoretically, right, if I guess you know, you could say you know, we know that here because we have this form where it's x squared plus y squared something is equal to some constant, right? So if x goes up, y has to go down. So they're coupled, right? But theoretically, you could have some sort of system, right, where you have an x variable and a y variable, and they could both be a function of time and do other crazy things, right? They may not be actually coupled. And so in that case, you know, you can't really use implicit differentiation because then, you know, x really isn't changing with y, right? Because they're both changing with other things. So the underlying assumption is that x and y are coupled. You know, they're functions of each other. Now the cool part is, if they aren't functions of each other, then you can do other solution methods if you're looking for you know, particular solutions that solve the problem. You can do things like a method of undetermined coefficients and things like that, which I think we've gone over. But anyways, I'm getting a little off topic, so let's get back to this problem. So this is how we would do it out. We just take we take d dx of every term, right? So let's go ahead and apply this, right? So here we have you know, d dx of x squared, so this is just going to be 2x, right? Plus, now here we have 4, we'll bring the 4 out front, right? Times dx of y squared. So how are we going to do this? We're just going to do the chain rule, because let's just take it as, let's just assume y is like some f of x, right? It's just some function of x. So if I was taking d dx of some f of x, and that f of x was squared, right? I would just do the chain rule, right? So I would do d f of x squared d f of x, right, times d f of x dx, right? That would be the chain rule, right? So we just take, you know, we take the derivative of the sort of the outside function with respect to that function, right? And then we take that function with respect to x. So this would actually end up being dy squared, right, dy, okay, times dy dx, okay? And of course we know d dx of 4 equals 0, okay? So this is what we have, and this is what we're looking for, right? We want the slope, we want dy dx, right? We want this term, right? So now this is very easy now, right? So we know that dy squared dy, well, this is just going to be 2y, right? So we have 2x plus 2y times 4, so 8y, times dy dx equals 0. So now we can just move the 2x to the other side, and so we'll get something like, and of course we can divide out, just divide everything by 2. We'll get, this is a 4, this is a 1. We'll move the x to the other side, so we'll get minus x, and then we'll divide by 4y. Right? And this is what dy dx equals. That's it. So the slope anywhere on this curve is just minus x over 4y, right? And the cool part is, if you were to like rotate this, or for some reason if you wanted to, if you had some function, maybe it wasn't like y and x, and you wanted to see, well, we know how y changes with x, well, what about how x changes with y? You can just invert this, right? So you can get, and you can go through the whole procedure again and show that this is correct. So you get dx dy equals minus 4y over x, right? And let's just check this to make sure that this is correct, right? So if we had x at minus 2 and y is 0, right? Well, if y is 0, this is going to be infinite, right? And same thing here, y is 0, right? Y is 0 right here, or x is 2, y is 0, because it's crossing the x-axis, right? The slope is infinite at these 2 points, just like we predicted. If we have 1 or minus 1, right, on y, well, our x is 0 because it's crossing the y-axis, so we have 0 slope at these 2 points, just like we predicted. And you can plug in any values of x, right, x and y, anywhere along here, and you can get the slope dx dy, right? And just as a quick sanity check, in this, let's see, in this quadrant, in the first quadrant, we expect the slope to be negative. In fact, in the first and third quadrant, we expect the slope to be negative. And it will be, because here both x and y will be positive, x and y will be negative, and we have this extra negative sign floating around in here. So the slope dy dx is negative. And of course, it'll be positive here in these two quadrants because x and y will have the opposite sign, and then we have this, so we'll have a negative from that. Then we've got this extra negative floating around, that'll make it positive. So another great, we'll go over this in another video probably, but another great question that a lot of textbooks ask, it's just good to know. Someone will give you a curve like this, or maybe a more complicated curve, and say, hey, tell me the slope of the normal line at a certain point. So like at this point on the curve, what's the slope of a line, right, that is normal to that point on the curve. So what you do, you use implicit differentiation, get the slope of the curve there, and then just invert that slope and make it negative, right? So if the slope here is 2, right, then the slope of the normal line is minus 1/2. Invert at a negative sign. So anyways, that's a good tool, a good thing to know. And we'll go over more of this implicit differentiation, and then we'll talk about how it gets related to the chain rule. Or excuse me, we already talked about how it's related to the chain rule. We'll talk about how it's related to related rate problems. We're just, because what we'll do is we'll start doing, instead of just generic dy dx, we'll do things like rate of change of volume, or rate of change of radius with volume, and height with volume, and I don't know, pressure with temperature, who knows, whatever. But you can do lots of great things with this, and then we can start doing optimization from there. So, anyways, we'll get to that. We'll get to that in a little bit, and I'll try to get these videos going. I know I was a little bit slow in the last few months, but we'll try to get these going a little bit more frequently in the coming weeks.